Welcome, everybody, to the Montreal chapter of the CSCA and to this month's public lecture on reductionism, emergence, and free will by our speaker, Erica Carlson. I'm your host, Joseph Vybihal. I'm a professor in the School of Computer Science at McGill University and the Montreal chapter lead of the CSCA. I'd like to, for those of you who do not know anything about the CSCA, I'll just do a quick introduction. I don't want to take too much time on this. We are the Canadian Scientific and Christian Affiliation. This is the URL for the website. The Montreal leadership team is chaired by me, and this is my wonderful committee. Electra, Andrew, Ron, and Maria. If you'd like to be part of the committee, or if you want to have or if you have any questions about the Montreal chapter, or you want to suggest speakers or topics, my email address is right over there. And so you can send me something there. If you want to be on the event email list, you can go to this URL. You'll see a form. You fill it out. We do not spam you. We just send invitations to talks. So you can do that. There's also a free blog that you can read up. We're on Facebook, YouTube, Instagram. And if you want to do a membership and you like more scientific stuff, there is a journal that comes with your membership. You'll also have access to our sister organization, the American Scientific Association. You can go to their URL over there as well. I will give you 1 second to write down anything that you want, like the email address or just the URL up here. I'll give you a second. Seconds up. So if you want any information, you can sort of talk to me after as well during the social time. So without further ado, right? So Erica Carlson is professor of physics at Purdue University. She holds a Bachelor of Science in Physics from the California Institute of Technology, as well as a PhD in physics from UCLA. A theoretical physicist, Erica researches electronic phase transitions in quantum materials. Ooh, there it goes. My screen just turned off. Oh my goodness. See, look at that. There we go. In 2015, she was elected a fellow of the American Physical Association for, quote, theoretical insights into the critical role of electron pneumaticity, disorder, and noise in novel phases of strongly correlated electron systems and predicting unique characteristics, which I dare you to say 10 times fast. Erica has been on the faculty of Purdue University since 2003, where she was recently named the 150th anniversary professor in recognition of her teaching excellence. And you can find her both in the great courses and YouTube if you want to hear her more. So that's it. So I will pass on this to you, Erica.
All right. Thanks for the invitation. It's great. It's great to be virtually with you. So I have been to Montreal before. It's a beautiful city. So I'm sorry I couldn't come in person, but thanks a lot for the invitation. And I'm looking forward to having a great discussion with you tonight. So I will be talking to you about reductionism, emergence, and freedom. The basic question being, are we bound by the laws of physics? And this is basically to get at the heart of what does it mean to be human, right? Are we humans really free like we perceive that we are, or are we just bound by the laws of physics and we can't be free? So what I want to start by thinking about, though, is, what is it that makes a physical law fundamental? How do we go about finding the deepest and truest things about our universe, right? How do I know when I've really found the most important stuff, for example? So we, for a long time, physicists were working under a reductionist paradigm in order to find out what what was the deepest and truest thing about the universe. And so this paradigm basically says, I'm going to reduce things to their smallest bits. I'm going to understand the bits. And then when I understanding the bits and how they work together, then I can build the whole thing back up and understand that. So what this looks like is, gosh, I'd like to understand something about matter. And so I'm going to take the matter, smash it to bits, find out what it's made of. And we did that. And we found out it's made of atoms. But you don't stop there, right? You keep going and you ask the question, well, what are the atoms made of, you know? So you smash the atoms to bits and you find that the atoms are made of protons and neutrons and electrons, and the protons and neutrons are in the middle in the nucleus, and then the electrons swarm around that and make a big fuzzy cloud. And we didn't stop there. We said, well, maybe there's other things in there, and we smashed the protons and the neutrons into each other, and we found that they're made of stuff. They have quarks inside, okay? So this is the reductionist way of going about understanding the world and trying to seek answers to what we think are the most important questions, and trying to find out the deepest and truest things about the universe. Now, along with this reductionist idea then comes the idea that the largest stuff we can think of, we can then reduce to its constituents, and then we think of those constituents, and maybe though they have components inside, so we reduce that and so forth. And so it basically implies a hierarchy of descriptions, right? So you might, maybe the bottom is strings. We don't really know, right? What's inside of quarks? Not sure. Maybe they're strings. So then the idea would be that the quarks and leptons are made of strings, that the atoms are made of quarks and leptons. Electrons, by the way, are leptons. And then the neutrons and protons are made of quarks. And so all those subatomic particles now are giving you the atoms. And then you put the atoms together, you get molecules. You put or you can put the atoms together and get materials, one or the other. And then out of those molecules or atoms, you can get many body systems, we call it. That's when you have a large hunk of matter. And then out of complicated molecules, you can make, molecular biology, and you can make cell biology, and then you can make, the biology of just a whole living system, right? And a whole organism. And then you could go and talk about, the physiology of it, and go up in psychology and sociology. And so the idea would be that you can not only start high up the chain and then come down by breaking things into their constituents, but you can go up the chain by understanding how the constituents interact. And so that's basically the reductionist philosophy of how to go about finding fundamental laws, how to go about finding the deepest and truest things about the universe. Now, one thing that we should be aware of is that this reductionist point of view really is ultimately a deterministic point of view. So, if we're thinking about the question of what does it mean to be human, the reductionist point of view would view humans as, well, we're made of parts, and those parts are made of parts, and those parts are made of parts, and you get down to the very deepest level, and we find that the atoms that comprise us obey laws, right? They obey physical laws, laws like electricity, gravity, quantum mechanics, and the thing about physical objects, right, is that physical objects follow physical law every time. That's why we call them physical laws and not suggestions. So these are pretty important rules there governing us at the atomic scale. And so this is ultimately a deterministic view of everything, because if we know the positions and the velocities of all the atoms in the universe, then we can predict their future, lockstep, right? Physical objects follow physical laws every single time. And so if you know everything that's going on right now, then you can predict the future. And in fact, if you take this very seriously as a view of what it means to be human, then it actually leads us to kind of some disturbing conclusions that I want to challenge. Okay, I don't want to leave us with this disturbing conclusions, but one disturbing conclusion would be that if everything's determined, if we're nothing more than a bunch of atoms, and those atoms follow physical laws, then these perceptions we have that we're free, for example, we have this perception that we can actually make decisions, and that we choose things, and when we choose, we legitimately choose. We weren't forced to. But the reductionist philosophy, the reductionist paradigm, the reductionist view of humans would say that, okay, but everything's actually determined, and so I can reduce you to a bunch of atoms, or maybe the better level to look at it to look at it for us humans would be to look at the level of DNA. So I could, say, look at your DNA, and I would say, well, I know from your DNA what your physical appearance is going to be. And maybe even from that, I can predict all your preferences. Maybe I can predict, for example, whether you're going to have ketchup or mustard on your hot dog, for example, or whether you're going to choose chocolate or vanilla ice cream. So the reductionist view would be that everything is determined. Those little atoms that make up our DNA follow physical laws, and then the DNA follows physical laws, and then all the other molecular structures in our body follow physical laws. And so if you take this far enough, you come to the conclusion that freedom, actual freedom to choose, must be an illusion. And I enjoyed very much reading this book by Susan Blackmore called Conversations on Consciousness. Susan interviewed a bunch of people working on consciousness. So she interviewed researchers. It's an interdisciplinary field. So this is chock full of neuroscientists and neurosurgeons and physicians and pastors and philosophers and theologians and sociologists. So it's a very interdisciplinary field. And she interviewed a lot of different people working in the field. And there were quite a few of that cross-section she took who came to the same conclusion that Susan Blackmore came to, which is that freedom must be an illusion, free will must be an illusion, and consciousness is an illusion. Now, why would you say that? Okay, you would say that if you think that everything is deterministic, right? If you think that everything is deterministic because we're nothing more than a bunch of atoms that obey physical laws, and physical objects follow physical laws every single time, that's why we call them laws and not suggestions, then everything that I'm doing is ultimately determined by the current positions and velocities of all the atoms in my body, and that's it. It's just going to be chemistry, physics leading to chemistry, leading to biology after that. That's that hierarchy of descriptions. And so kudos to Susan Blackmore for putting it so starkly, right? I mean, I think she's right about that. I think she's right that if we are nothing more than atoms, then that's right. There's no wiggle room there left for freedom. Now, you might think, okay, but this seems a bit odd. We all have this impression that we have freedom. Is there some place it's coming from? Where could we get true freedom? Is it possibly hiding somewhere in the laws of physics? If we look from the right angle, for example. So one idea that people have put forth is maybe quantum mechanics gives you an out, right? So maybe quantum comes to the rescue. Now, I like that because I like quantum mechanics a lot, and it's a really fun theory to think about, and it's a very useful framework. I mean, quantum mechanics has been confirmed to several places of the decimal. It works. It's really there, right? And so there's a little bit of indeterminism in quantum theory in the sense of we can't predict everything. We can predict some things, but certain other things we can only predict at the probabilistic level. And so the idea here would be that individual quantum events, okay, individual things that are happening at the atomic scale are governed by quantum mechanics. And so there's a little bit of probability to the outcome. And so, if that makes you nervous, by the way, you're in good company, because this is one of the things that made Einstein nervous about the theory of quantum mechanics. He had many things to say, but one thing he had to say was, well, God doesn't play dice. There's something strange here, okay? But ultimately, he thought perhaps it was an incomplete theory, that maybe there's something more there that we just haven't discovered yet. Richard Feynman, Nobel Prize-winning physicist, had this to say. You have to imagine this in his lovely Brooklyn accent, okay, talking about quantum mechanics and the fact that we describe things with probabilities. He said, you don't like it? Go somewhere else. Maybe to another universe where the rules are simpler and more philosophically pleasing. All right. So physicists acknowledge that quantum makes us uncomfortable. All right. It's really fun to think about, and it's a very useful theory, but it makes us uncomfortable at some level because we use probabilities to describe it. Now, there's a couple of issues with that. If you want to think of the quantum probabilities as a way to get us back to some sense of freedom, there's a couple of problems with this. One is that we actually don't know if physical objects really are having just random events. It's an open question whether that we're using probabilities simply because they follow the same statistics as the physical object, Okay, and there's some underlying theory below that that's going to be deterministic. We don't know that yet. But another issue is, but it could be that the physical objects themselves really are following little dice rolls. Okay, maybe the fabric of the universe is inherently probabilistic. So another issue you come up against is that large objects still end up being deterministic. And it's because large objects are comprised of so many quantum particles, and so many quantum events would have so many dice rolls that the whole structure becomes deterministic again. So if you think about it, this is actually how casinos make money, right? I mean, in fact, you mentioned that I'm a fellow of the American Physical Society. The next big meeting for us that I go to, the one that's about my subfield, is happening in Las Vegas, so we'll be seeing the casinos there, right? And so casinos make money, right? They're in the business for money, and yet they depend on all these little dice rolls or cards or things that are ostensibly random, right? And the thing is, the way they make money is because there's enough people playing the games enough times that it becomes deterministic again. So any single roll of the dice, no one can predict the outcome. Okay, and then I have to tell you, you could in dice actually aren't technically random. If you really had a great little high quality, high resolution video of exactly how the dice left someone's hands, then you could, using all the laws of physics, make the predictions about exactly how they would land. But that's a little hard. So everybody just pretends that dice are random, right? Because they come up with uncontrollable answers. So casinos still make money anyway, right? They don't know the answer to the dice you're going to roll. Nobody knows. It just happens, right? But if you roll the dice enough times, and if you roll 2 dice enough times, I don't know what you get on any roll, but I do know how frequently you're going to get snake eyes. I know how frequently you're going to get double sixes, okay? And that frequency becomes more and more precise the more times you roll. So that's how casinos make money. The whole large scale thing there is deterministic as far as the averages go. The other serious problem with trying to let quantum indeterminacy, quantum randomness, get us back to some sense of freedom is that it's sort of the opposite of free choice, right? Random chance is not choice. When we talk about humans having freedom, we have the impression that we make decisions, we make choices, but little atoms now subject to all these random forces is kind of worse, right? It's not better, it's worse. It doesn't offer a proper solution to this question of, well, how is it that we humans perceive that we experience true freedom and can make choices? Now, another thing that you might think could come to the rescue is a relatively recent way to look at things in science, and that's emergence. And emergence is something discussed in a lot of fields. It's well grounded in my field of condensed matter physics, which I'll tell you a little bit about a little later. And Bill Newsom, who's professor of neurobiology at Stanford, had this to say. He said, "I suspect that answers will ultimately lie in a deeper understanding of emergent phenomena in complex systems." So we'll unpack that a little bit and see where we get with that. You should know, by the way, that Bill's a believer. Now, reductionism got us a lot of mileage. Okay, so when we were thinking out of the reductionist philosophy, we learned a lot of things, right? We learned what material is made of. We learned that they're made of atoms. We learned what the atoms are made of. We got a lot of mileage out of this philosophy of breaking things into their smallest bits. But it turns out that there are some questions that are important that reductionism just isn't tuned to answer. So here's a good example. I'm showing you the Mona Lisa, and what my art history teacher told me is that she's special because she's smiling in a very peculiar way. She's smiling with her eyes. And so you could ask the question, how did Leonardo da Vinci do that? How did he make it so that she's smiling with her eyes? Now, the reductionist philosophy gives you a strategy for answering that question. The reductionist would say, oh, I know how to answer this question. Let me scrape a little paint off of that. And at which point all the art lovers in the room gasped in horror, right? And so maybe we won't scrape it off where you'll notice, just a little corner where nobody's going to notice. We'll scrape off a little bit of the paint. We'll do a chemical analysis on the pigments. And then we're going to answer this question, because that's what reductionism does. It drills down to the bottom, right? And finds out what the constituents are. Now, how many of us think that you could answer the question, why is Mona Lisa smiling with her eyes? How many think that we could answer that question by doing a chemical analysis on the pigments? It's not going to answer that question, right? So we come up against this wall that reductionism fails to answer many important questions, okay? So maybe emergence is a better strategy. So let me tell you a little bit about sort of the opposite philosophy of reductionism, which is emergence. And that's very well grounded in my field of condensed matter physics. It comes up in other fields as well. In my field, we have exquisite control over it, though. So we can write down, we can write down all the mathematics associated with it. That's called renormalization group, if you want to look it up. Ken Wilson won the Nobel Prize for that. And then we have it backed up by experiment. So we have a really good handle on it the whole way through, all the way from the small bits to the large bits. So we have a good handle quantitatively on emergence in my field. So what's my field of physics? My field of physics is condensed matter physics. And we mean condensed in the sense of condensation. So gas condenses to liquid, liquid condenses to solid. We're ultimately about the study of phases of matter and phase transitions, but basically we're about objects that you can hold in your hand. If you can hold it in your hand, it's the domain of condensed matter physics. A star is too large to hold in my hand, right? There are other reasons you can't hold a star in your hand, but a star is too large. An atom is too small. I mean, I'm technically holding a lot of atoms, so many that I can't really touch them, right? So if it's about the size of something you hold in your hands, then it's the domain of condensed matter physics. And so we could ask questions, now, like, okay, well, let's think about some condensed matter systems, okay, and how. So condensed matter systems, like I said, are things you can hold in your hands. I like minerals a lot, so let me show you some things about rocks. Maybe you have some favorite rocks. So here I have some fluorite, all right, and it's a very beautiful crystal. And we're big fans here of going to a store nearby that has a lot of beautiful mineral samples. So my sons and I go buy beautiful mineral samples periodically, and we could ask the question, why is this fluorite hard? Okay, we could ask that question. Now, the reductionist has a strategy for answering that question. The reductionist would say, give me that fluorite, I'll break it into its smallest bits, we'll find out what's in the bits, and then that'll tell us why it's hard. So the answer here that a reductionist would give is that, okay, it's fluoride, it's made of calcium and fluoride. So it's hard because it's made of calcium and fluoride. Okay? Now, all right, that's all right. Here's another of my favorite rocks. Okay, this would be sort of my favorite rock. That's from my husband when we got engaged. That's a diamond. And diamond is also hard. So if we ask the question of, well, why is diamond hard? The reductionist philosophy would say, break it into its bits. It's hard because it's made of carbon. But the problem there is that, well, this was also hard and there's no carbon in it, right? And this is hard, but there's no calcium or fluoride in it. So this answer that it has a property because of its constituents, because of what it's made of, is actually inadequate, right? So the reductionist would answer, here I've got a nice picture of quartz. The reductionist would answer, well, that's hard because it's made of silicon dioxide. But ultimately, when we're seeking to find answers, we want answers that have the broadest explanatory power, right? So it is true that this is made of calcium and fluoride, and this is made of carbon, and the minerals I'm showing you now are made of silicon dioxide, and the one on the right is a beautiful specimen of bismuth. There's another answer you could give, which is that they're hard because they're crystalline. Crystalline, what does crystalline mean? It means that the atoms inside have gone into lockstep arrangement. They have formed what we call a crystal. There's a regular periodic arrangement, just like the tiling on your floor is a regular periodic arrangement. And anytime we see atoms go into a regular periodic arrangement, no matter what type of atom it is, every time atoms go into a regular periodic arrangement, you get crystallinity, you get hardness. So the better explanation for why those materials are hard has to do with the organization. Okay, it's something at the organizational level, and then the hardness emerges out of that organizational level. Now, how do you know you're dealing with something that's emergent? So I've just argued to you that hardness is an example of an emergent property, because the answer to the question of why is it hard wasn't contained at the atomic level. It's not because it's made of carbon. It's not because it's made of calcium or fluoride. It was because of some larger scale organization. So how do you know you're dealing with something that's emergent? Emergent phenomena occur at the large scale when you have many constituents interacting together, and you get some new phenomenon that arises in the collection of constituents that has no counterpart in the smaller bits. So here's another example of that. So here's some water, okay, in a pitcher. Now water And, in our everyday lives, water can take on lots of different forms. This happens to be liquid water because it's out here at room temperature, and liquid water at room temperature and pressure water at room temperature and pressure is liquid. It's not solid or gas. And one of the properties of it is that it flows. Okay. So here it's flowing into this glass. So it's liquid, and it's also wet. So how do you detect that it's wet? Okay, so the way we would do it in our everyday lives is to just touch it. It feels wet. Okay, so there's a property here of wetness. But if I were to hand you, rather than handing you a glass of water, if I handed you one water molecule, where did the wetness go? Or if I handed you one water molecule, could you say it's a liquid? You couldn't, right? One water molecule doesn't make a liquid, and one water molecule doesn't have any wetness associated with it. When you want to talk about wetness or liquidity, you need to have a collection of particles. It needs to be a large collection of particles. By the way, anytime you can hold something in your hand, you have at least an Avogadro's number of particles in there. And so to remind you what Avogadro's number is, it's 6 times 10 to the 23. That's 6 with 23 zeros after it. That's about a billion times a billion times a million particles. It's a lot. So when you have a collection like that, now you can start to talk about these emergent properties. Wetness and liquidity are something that I can't observe in a single water molecule. I need a collection of them to come together, have a particular organization to them, and then the wetness and the liquidity emerge out of that organization. And I've got here a picture of people doing the wave. Has anybody ever done the wave in a stadium? Okay, all right. So, and that's really fun, right? So if you've ever been to a baseball stadium, or sometimes people do it in like soccer stadiums, whatever, the crowd raises and lowers, and you see this wave come about, and the wave is an emergent phenomenon. Okay, so it happened at the macroscopic level. It didn't really make sense to talk about it at the level of one person or two people. I know this because my friend and I in college tried to do the wave when there were only 2 of us in the stand. Caltech was a really small school, and so we went to support the water polo team one day. We were the only 2 people in the stands, and we said, we're going to do the wave. And it's as lame as you're thinking. It was just that lame. Just 2 people, it just doesn't work very well, right? So it's something that arises in a large collection of people, and it's independent of the constituents. It doesn't matter whether they're doing the wave in Montreal or Boston or Rio de Janeiro in a soccer stadium. It's gonna be a wave, right? So there's something emergent that is not contained in the constituents, even though it's carried in the collective of the constituents. Now, other examples of emergent phenomena that you'd be familiar with include, for example, well, we talked about waves. So waves that are happening in a medium, such as people, or water waves, since I have some water here, are examples of emergent phenomena. The waves, you're hearing my voice right now through sound waves, and those are collective phenomena in the air. Wetness and hardness, we said, are emergent phenomena. Other larger scale emergent phenomena would be things like our network of roads, right? And government structures and the need for money, right? If an alien had only met one human being, would the alien predict that there are some countries that are democracies and some countries that are monarchies? Would the alien predict that we need, the dollar and the euro? These kinds of things are hard to envision just from a single constituent. But when the collective gets together, certain behaviors emerge at the collective level, and that's emergent, right? So the question would be, what can we learn then from emergence? All right, so let me tell you some lessons we can learn from emergence that I think help clarify some of the issues and what does it mean to be human, and in particular, do we really have the freedom to choose that we perceive that we have? So here are some things that we learn from emergence. Lesson 1, we learned that new entities arise at new levels. So new properties, for example. So the property of wetness, so the property of hardness, or even the wave itself. These things were arising at new levels. Lesson number 2, actually, is that new laws arise at new levels. So once I tell you that the water is liquid, I can start to talk about laws of liquidity, okay, which include things like wetness and surface tension. Once I talk about hardness, right? If I talk about the fact that this crystal is hard, I can write down laws concerning the hardness and how it behaves under certain circumstances. So new physical laws emerge at these new levels as well. So one implication that I think emergence gives us a good cause to take to heart is that we can and we should take high-level observations seriously. So observations that are made at these levels of the collective are meaningful and can in fact shed light that's not they can shed light and give us information about things that are not accessible to us at the level of the constituents. Some other things that emergence teaches us, we also saw already that different microscopic situations can lead to the same macroscopic situation. So microscopic would be the level of the tiny bits. Macroscopic is large, so it's the level of the collective. And we already saw that different microscopic situations, for example, different atoms inside of a crystal, whether this is calcium and fluoride or this is carbon, they're different microscopic situations, and yet they led to similar macroscopic situations of crystallinity and hardness. And other examples of that are when you see a wave happening in a medium, such as a sound wave or a wave happening on water. Every time a wave comes up like that, it follows the wave equation, and we get to use all of our lovely wave equations for it. And so these different microscopic situations can lead to the same macroscopic situation. So reductionism can't necessarily explain why the high-level behavior is occurring. The high-level, that's because reductionism would only give you the one answer that you have in hand, right? It would answer the question of hardness by saying it's hard because it's made of calcium and fluoride. But we saw that wasn't quite right. We needed to study more systems and to understand things at the collective level in order to answer that question. So, those are some of the big ideas in emergence. And so we could ask the question, is emergence a better strategy, right, for understanding what it means to be human, and particularly this aspect of freedom that we all perceive and the aspect of free will? So is emergence going to be a better strategy? Bill Newsom suggested to us that it might be, right, especially as it regards our consciousness and things that we perceive, that we make decisions that are actually free. But a word of caution, right? A word of caution is that the reductionist philosophy, though, like we said, it failed, okay, because of the determinism at those levels. Emergence, let's see what emergence is going to do for us, all right? So one thing we should be concerned with is that the known examples of emergence where we can track the whole thing, where we have a good quantitative understanding of it from top to bottom, such as in this crystal or such as in the liquid, those condensed matter systems, where we can write down all the mathematics that shows you why the emergence happened, and then we can test it in a lab, and so we know it's correct. Those known and understood examples of emergence are all deterministic. Water is liquid every time you have it at room temperature and pressure, right? Every single time, it's liquid every single time. So, crystalline materials are always hard every single time. And determinism isn't freedom. So if we're just going to rely on emergence, we're just going to push the problem to another level because, like I said, the known examples of emergence are all deterministic. So are there other lessons we could learn, though, that still might help us disentangle this? Other lessons that we learn from emergence, lesson number 4, that large-scale phenomena can be, in some sense, independent of the constituents, okay? Once the large-scale phenomena arises, you no longer need to talk at the level of the constituents to describe it, right? Every time a wave happens in a medium, whether it's a wave on water, or a wave in a sound wave in air that you're listening to right now, or the wave in a baseball stadium, a wave is a wave is a wave, and it's got its own description. So these large-scale phenomena can in some sense be independent of the constituents, right? Like we said, the wave in a stadium didn't matter whether it was who was doing it exactly. It didn't matter whether it was people in Montreal or people in Rio de Janeiro. In some sense, the constituents are interchangeable. Lesson number 5 actually is about causality. Causality can flow not just bottom up. That's the idea, the ultimate idea of reductionism was that by drilling down, you understand the constituents, and then the reverse idea that you can build things back up. Constructivism really is as the idea of building things back up. The idea being that the causality is coming in at the lower levels and affecting the higher levels. But we actually know that causality can flow top down as well. All right. And one of the ways we know that, even from my field, is kind of implicit in how the experiments are done, right? All the experiments are set up by experimenters, set up by people who are scientists, who put the physical systems into the circumstances they wanted. So you're absolutely using top-down causality in order to discover all of these emergent phenomena in the first place. So causality can also flow top-down. So these are all important observations. And then lesson number 6, all right, is that not all large-scale structure is emergent. I've focused on emergent behavior, but we all know of examples of large-scale structure that's actually not emergent. It didn't just arise because the collective got together. It was superimposed. So, for example, if you walk into my house, and it's your first time there, and you come into the foyer, and then you say, "Oh, look, what an interesting floor plan. Notice how the foyer flows into the living room, which flows into the dining room. That's a very nice floor plan. It must be because you built the house out of Indiana limestone," right? That's not quite it either, right? So there's a large-scale structure to any house. That's the floor plan. But no one thinks that the builders just made it that way by throwing the bricks up in the air and then boom, they sort of self-assembled and this house emerged, right? In that sense, there are certain large-scale structures that are imposed, right? There can be transcendence. There can be something that's imposed from the outside, this top-down causality being written into things. So floor plans of a house, for example, are not emergent, right? You can build the same exact floor plan whether you're using bricks or wood or Indiana limestone. So not all large-scale structures emergent. Transcendence happens. So we're up against then this question, right? So this was the challenge that I wanted us to, this was the statement that I wanted us to challenge. The statement to challenge being reductive determinism precludes free will. Okay, and it does. If you want to view humans as nothing more than atoms, you want to really be serious about your reductionism and your determinism, that precludes free will. Therefore, free will does not exist. Put a circle around that therefore, because that should give us pause. And one of the things that's going to give us pause is the ice cream store. Okay, around here we have a great ice cream shop. It's called the Silver Dipper. They have lots and lots of flavors, and my family loves going there. And it's great watching your kids try to decide what to get. We're all tasting things, and I have a hard time choosing between their triple chocolate chunk brownie and Snap-a-Lantern. Snap-a-Lantern is a lovely seasonal ice cream around here that's made from pumpkin ice cream, and then they have bits of gingerbread cookie in there. That's an awesome ice cream. But trying to decide between these is gut-wrenchingly hard. But I do believe that when I finally make the decision, that I really have chosen, right? And it was a free decision. So we have this high-level observation, right? High-level observation that we make free decisions, that we have free will. And so that, if we take seriously that high-level observation, then there must be something wrong with this line of reasoning, all right? And I think that what emergence can contribute to this discussion is all those lessons I told you that, and one of those lessons is that high-level observations are meaningful. We shouldn't throw the baby out with the bathwater. So, for example, right, if free will really is an illusion, if consciousness is an illusion, then here's the problem, right? If my brain is lying to me about something that fundamental, why should I trust my brain about anything else it tries to tell me is real, right? You should sort of lose confidence in the entire system if there's that much, if it's that wrong about something so important. So then, we're back to this question, are you really just a bunch of atoms? But I think our high-level observations of freedom are important. And that basically takes us to, maybe we should think about this in terms of something beyond emergence, right? In the same way that there is some transcendence that we see even in the floor plan of a house. The floor plan of a house isn't contained in the bricks. It's not reducible to the bricks. It also didn't emerge from the bricks. It's not like the builders threw the bricks together, they self-assembled into the floor plan. There was something imposed there. So I think that the last implication I want to bring up is that if we put all of this together, then we're drawn to this conclusion of, if we take seriously our high-level observation that we have freedom, and I think we should, then there must be something more than the physical world, because purely physical objects follow physical law every time. That's what physical objects do. They follow physical law. So this brings us up to the idea that there just must be something more to this physical world. Now, will science ever give you a good reason for why that might be the case, or will science even be able to treat this question? No, we're now beyond the road. It's no longer a scientific question. We're moving into philosophy. Okay. But I do think that Christianity offers a good explanation to this, a good resolution to us, which is that there is more to us. Okay. So maybe in the same way that there's more to, the Mona Lisa, right? The light in her eyes we saw wasn't explainable by reductionism. It also wasn't explainable by emergence either. It was explainable by the transcendence of the artist who painted the men. So in the same way that the light in her eyes is really something transcendent, maybe the light in your eyes and the light in my eyes is something transcendent, coming from something beyond the physical world. And the Christian answer to that would be that we have a creator. So I'll just leave you with this quote from Hamlet, and thanks for your attention. And I look forward to your questions.
Okay, so I just wanted to know, usually science doesn't postulate things unless there's any empirical evidence for it. Right. Science doesn't detect any kind of mental substance that arises from brain activity, for example. Okay, the only thing that brain activity science detects is electromagnetic fields being generated from the movement of ions in the nervous system. Mm-hmm. So why postulate anything at all that the mind emerges from brain activity, or the sum total of all activity in the brain that includes other things besides the movement of ions, including the neurotransmitters or anything else? That's my question.
So let's see if I understand the question. I think the question is, science doesn't directly detect the mind anyway. So actually, I don't quite understand the question yet.
So why postulate that brain activity is generated in the mind? Why not just say the mind is the brain, or perhaps we exist independently from our brains and bodies, as Descartes and Plato believed, and most Christians would believe, and that we're interacting with our brains then?
Yeah, well, okay. So this is great, and of course, we're moving now into philosophy of mind, and we have to remind everybody that I'm not actually a philosopher. But I agree with the way that you've phrased it. I think one of the important things is to keep in mind what we can and cannot measure. Can we directly measure the mind? I don't think so. We can, but we have different ways in which we can do measurements, right? So you mentioned the electrical brain activity. We can also make measurements on people's reporting of their own perceptions, right? So you can take data on what people perceive, right? So it's harder and a little harder to do the quantitatives on that. So I think there's several levels at which you can explain it. I do agree with you ultimately that when we really get to issues of exactly what is your mind, I think we should say, as you have said, that it interacts with our physical system, right? There's an interaction between the two, but that the mind is not reducible to the brain. But that's not necessarily the framework from which most scientists who study the brain at the level of the physical system, that's not the view that they're typically taking. And part of that may just be the limitations of working such a complicated question from only one field, right? Okay. It really is a question that demands a lot of fields come together and have a robust discussion. Okay. I didn't really answer your question other than
that's okay. But I mean, would you say that you are moving your mouth right now and you're stimulating your vocal cords and moving your tongue and moving your eyes and so forth, or do you think that's totally under the control of physical chemical forces in the nervous system?
What's my own view of all this stuff? So my own view would be the Christian view of this, that we're not just physical objects, that God created us in His image. And part of being in the image of God is that we have a spiritual component to us. There's a part of us that's eternal, and that part of us, because it's eternal, can live on beyond this universe. So that part of us then transcends this universe. And so, the Christian view would be that these interact, right? The spirit interacts with the physical.
So you believe you are moving your mouth right now? You believe you're moving your mouth and your eyes and you're moving your shoulders right now?
Absolutely. I believe it's me doing that, and that the me I'm referring to is the spiritual me who, will transcend this universe. Absolutely.
Okay. Yeah. Okay. Thank you so much. Someone else could ask questions now. Thank you so much, and that was a great talk. Have a great evening.
Thanks.
Okay. There's someone in the chat. So Raynand wrote, can you comment on how we can integrate this type of thought in science education?
Oh, well, that's a really good question. Well, parts of it, you could integrate it, like all the whole emergence discussion. I'm, as a condensed matter physicist, I'm all gung ho about seeing that integrated everywhere. But I think you mean more the questions about what it means to be human. I think you can lay the groundwork in how you do science education. Okay, so I think when you really get careful about philosophy of science, I think it's extremely helpful for people to be aware of the limitations of the scientific method. We love the scientific. I love the scientific method, right? So I do this stuff for a living. It's my bread and butter, right? But it does have its limits. You can't answer every important question. So in the same way that I argued, you can't answer every important question with reductionism. You can't answer every important question with the scientific method. For example, if I wanted to know what my husband's thinking, right, I should just ask him. I shouldn't attempt to do an experiment on him without, that's not the right way to do it, right? So there are limits, right? And the scientific method, when we're doing it, okay, so now I'm going to give you my perspective as a Christian who's a scientist. How do we put all this together, and what does it mean to do the scientific method as a Christian? So now I'm going to wrap some theology around that for you. Okay, so I do believe that when God created humans, right, the account we have in Genesis is that he created Adam and Eve, and then he blessed them. He said, be fruitful, multiply, fill the earth and subdue it, rule over the fish of the sea, the birds of the air, and the creatures of the land. He gave us authority over earth and told us to take good care of it. I believe that by extension, when he did that, he gave us authority to discover physical law, because we would need that authority to discover physical law in order to take good care of creation. So when we go into a lab and do the scientific method, I believe that because we've been given authority over the earth, we've been given authority over that system, and so we can apply the scientific method to it. Let me contrast that with, say, trying to find out something about the spiritual world, right? When you talk about the spiritual realm, you're talking about personalities. You're talking about God or the spiritual part of humans or angels. So good luck getting the angels to sign your paperwork to do a randomized controlled trial, right? You're not going to get that through your IRB board at your university. So there are limitations to the scientific method. It can't answer all of the interesting questions that we want to answer. And so ultimately, I have posed a very interdisciplinary question. So I think teaching students, when they're learning science and learning the scientific method, teaching them the limitations of the scientific method, I think, is important. So, for example, one of the ways this comes in as a Christian doing science is so I'm a theorist, I just use pencil and paper, but my colleagues who are experimentalists, when they go into the lab and measure something, we are all working under what's called methodological naturalism, okay? I don't think that naturalism, meaning that nature is all there is, the physical world is all there is, ultimately materialism, I don't think that's the right worldview to explain everything we observe. But when we're studying limited physical systems, because of this limited authority that God has given us to uncover physical law, I believe the right thing to do is to work under methodological naturalism, meaning I'm going to assume that I'm in full control of that physical system. And so I've set things up in a way that they're going to obey the physical laws that God gave them, right? God gave these little particles physical laws, and I have been given authority by God to discover them. So, that's all a good framework to work within. And anyway, that's where I think you would kind of hook it into science education, would be the limitations of the scientific method are something that we can and should teach.
All right. Next question is coming from Robert Mann.
Yes, hi, thank you. Quite an interesting talk. I have a lot of questions about what you mean by transcendence or what you mean by, how do we know anything is emergent? But I'd rather ask this. You said you thought you were a transcendent being. Do you expect that we will one day either be able to invent an artificial intelligence that you would contend is as transcendent as you are, or alternatively, upload your transcendence into some form of silicon?
I love it. I love this question, and the short answer is going to be I have no idea, but I think this is a brilliant question, and I'm also curious about the answer. Let me be a little bit more careful and try to define transcendence in the way I was using it. That might help clarify. So I said that the floor plan of a house involves transcendence, meaning the architect is what's transcendent. What's transcendent is the architect who designed it, and then the builders who build it are transcendent in the fact that they're outside of that physical system, and then they manipulate it. Similarly, Leonardo da Vinci transcends the Mona Lisa. He's separate from it, and he interacted with that physical system right through his paintbrush, but the transcendence is coming from some higher power. And so I think in the sense of human beings, the way to extend that analogy would be that there must be something transcendent about us. I don't necessarily mean that I'm transcendent, but I would say that our creator is transcendent and imprinted this into us. Does that kind of help clarify at least the transcendence part?
Well, it does. I would elaborate in a further way, differently. By the way, I'm also a theoretical physicist.
Oh.
But in any event, why don't you go on and answer whether you expect.
Sure. Well, I apologize for the lack of equations in this, but
that's all right.
You're surely familiar with renormalization already. So I'm just going to give you my opinion on this. Now, I actually work on a little bit of artificial intelligence, as a lot of groups do nowadays. We incorporate machine learning into what we do. So we run neural nets and things like that. I do not believe that we will ever, as humans, create some artificial intelligence that then itself becomes self-aware and has actual freedom to choose. Because those AI systems, they will be able to mimic. Here's what's going to be difficult, right? They will be able to mimic us like crazy, and it will probably spook us out, right? So I believe we will be able to create systems that are such good mimickers that we may have trouble. However, ultimately, those, let's say we encode it into silicon or something like that. Well, the silicon is following, physical laws, and the software that's in it is following physical laws. So like right now, for example, how do I use a neural net in my research? A neural network code is something that's designed to learn in a very limited sense. So you write the code, and then it's going to follow certain rules as to how it learns. So basically, you present it with stimuli. It changes some of its own parameters in a completely deterministic way, by the way. Changes some of its parameters. And then now it's a new version, and then you present it with new stimuli, and it changes some of its parameters in response. And so it basically learns in a way that I couldn't hard code in the beginning. But the whole thing lockstep is deterministic, and will always, as long as it's occupying a physical system, I don't see how we're ever going to get out of the fact that physical objects follow physical laws every single time.
What about uploading consciousness into a computer?
Yeah, that's a great question. I just think you can't. I think you can't, because how would you even read it? I don't know. But I guess if you postulated that you could have, we're going to have to go to neuromorphic computing, by the way, now, right? So neuromorphic computing is going to be, like you say, going to upload a consciousness into a computer. Silicon's not going to cut it. Silicon doesn't act like the brain. So you need some hardware that's going to act like a brain. So let's say you had this neuromorphic, architecture for a computer. It's going to have little things that act like neurons and synapses and things like that. So aside from that issue of how do you go about transferring the memory over, it's still going to follow physical laws, right? It's still going to follow physical laws. So it can't, there's no freedom there. There's just no freedom to choose. So
are you saying, sorry to be a debate, are you saying that you think our brains do not follow physical laws?
That's a great question. Okay, so I think our brains are subject to physical law, but because, and here I'm going back to the Christian worldview, because the Christian worldview of a human would be that there is something more to us than the physical, that there is an invisible, immaterial part that we call spirit, and that spirit interacts. Then it's like, I can't resist because you said you're a theoretical physicist. So let me talk in terms of Hamiltonians, okay? So a Hamiltonian is this equation, is this expression, mathematical expression we write down that includes all the energy terms that are coming into a system, okay? We like to track energy because it's a good number. We can always track it. There's conservation of energy. It's good stuff. Now, so I would say if you were going to write down, say, the Hamiltonian of how my brain works, you've got all the purely physical terms. It's absolutely following physical law, right? Neurons follow physical law. But then there's this other interaction term, whether it's interacting with the spirit realm. I think that term is there, but you can't access the spiritual to measure it. So you can only access it indirectly through the whole behavior of the system, which is why I'm saying that we see this free will phenomenon that we all observe at the high level. Okay. I think that's evidence that there's this interaction term between our physical brain and the spiritual world. Does that kind of help? I mean, I haven't proved that.
Does partly.
Okay, I'm going to
anyway,
interrupt.
others probably have questions.
I'm going to
so I better
interrupt.
stop.
Yeah.
See, I actually do artificial intelligence, so I'm kind of biting at the bit, but I'm going to move on to Steve Bushell, and then there's someone on the chat as well. So Steve.
Okay, but later during the social time, Joseph, you have to give us your take.
Well, thank you very much. A fascinating discussion. I now understand much better the term emergent as it applies to physics. I had seen and read of that term before, but now I think I have a little bit better grasp of it. But Dr. Carlson, I wanted to ask you because there was a paper I read a couple of years ago, a year or two ago, I think, about talking about emergent gravity, the whole concept of emergent gravity being something that, if properly interpreted, might negate the need for dark matter, which is the thing we hear lots and lots about. And it seems like, to me anyway, it's just like, okay, things are moving a certain way. We don't know why. Let's just call this thing dark matter and let's just assume it exists. But I just wondered if I hadn't heard anything for quite a while about this emergent gravity theory. And I just wondered if you knew anything about that, because it just sounded fascinating to me.
Yeah, I wish I did. That sounds really fascinating. And this is the first time I'm hearing about it from you. So I really shouldn't comment on it, especially dark matter is not my field and cosmology is not my field. But I mean, just from a general framework point of view, though, this is the whole emergent issue does ask question, does kind of beg the question of will you answer the questions you want to know by going deeper into the particle physics world, right? So one of the things we learned from emergence is that in some sense, once you had emergent behavior, that emergent behavior, the same emergent behavior, could have come from several different physical circumstances, right? All crystals are hard, okay? But what is this idea to drill down to the bottom of things talking about, right? It's trying to go down to the bottom and find the atoms and find the protons and neutrons and find the quarks and look for the strings. But once you get the quarks, does it matter that they were made of strings? So you have this question of, well, if things are just going to emerge anyway, you may as well just start with what you have in hand. You know what I mean? In some sense, going down to those deeper levels, once you go through one level of emergence, you've got kind of a shield, right, between what emerged out of it and what's below. You can't from the emergent behavior find out what was below. And in some sense, it doesn't matter, right? So I think it's something important. I'm really glad to hear that it's being discussed in terms of gravity, that emergent ideas are being discussed in terms of gravity. I think it's an important concept I'm excited to hear. I'm excited to hear about it, and I don't know any answer to the question you asked.
I'll have to Google it. I think it was out of Scandinavia. One or two scientists out of Scandinavia a year or two ago, and then I haven't heard anything about it since. So I just wondered if you had. So thank you.
Yeah.
All right. So from the chat, there's Joshua Harris. He goes, I wonder if you would agree that there is an even more basic logical problem with views such as consciousness is an illusion, namely that illusions are the sorts of things that can happen only because someone who is conscious is deceived, makes a mistake, etc.
Okay, so let's see if I understand sounds more like a statement to me that one of the sounds like what you're saying is that one of the problems with saying that consciousness is an illusion is that one of the problems with then illusions is that you're being deceived, and so how do you know you're conscious in the first place? Is that kind of the question? Oh, it's in the chat box. I can look at
it. Chime in. Sorry about that. Thank you so much for your talk, by the way. The question is, well, I mean, this is something, I'm a philosopher, right? So
good. Okay, that's why I didn't understand your question. So use small words, okay?
Yeah, well, I don't know. Well, physicists use their sharp big words. The basic idea is like, well, okay, if you're going to say consciousness is an illusion, right? Illusions are the kinds of things that require someone conscious to deceive. It doesn't make any sense to say that consciousness is an illusion. It's like saying that you can talk about numbers without talking about oddness and evenness. It's part of the package, right? So I just wonder. I don't know. Maybe this is the first time you're hearing of this criticism. It's something that was made famous by Wittgenstein and others. And I just think it's a really big problem. I think it's a big, red, throbbing problem with this idea that consciousness is an illusion. And maybe it's just something that can be part of the package going forward in terms of criticism.
Nice. Okay. And who was the author there? Wittgenstein with a V? Well,
Wittgenstein, but I think most philosophers would agree with that. Like, there's not much consensus in philosophy, but I have to say that that's one of the basic items. I mean, because what would it mean? What would it mean to be deceived if you're not conscious? You have to be conscious to be deceived, right? Mm-hmm. And that's the point.
I see. So it sounds to me like it's sort of falling in the category. Again, I'm not a philosopher, but it sounds like it's sort of falling in the category of a self-defeating statement. That the statement consciousness is an illusion has a problem even just at the statement level, that it wasn't really a well-defined statement because to be deceived is to be conscious.
Yes, I think that's what I'm trying to say, exactly.
Okay. Yeah, that's a nice argument. Thank you.
All right. So I think I will call this to a close. Thank you, Erica. That was a fantastic talk. Lots of discussions about it.